Good morning. Today's topic of discussion is gravitation. Okay, as you know, gravitation is a very important chapter in mechanics, and every year in medical or engineering entrance examinations like JEE Mains or JEE Advanced, every year at least one question is asked from this topic. Okay, so this is a very important chapter and obviously interesting. So we will start this chapter today. You know, in gravitation, just before studying the gravitation, actually we study a lot in this chapter mostly about the heavenly bodies, the planets, their motion in their orbits around sun, the satellites, natural, artificial, and so on, right? But the basic thing, the gravitation, the gravitational interaction. What do you mean by the term? Exactly, gravitational interaction is the interaction between, gravitation is an interaction between two mass particles, two or more between the mass particles, between the masses. Okay, this is the gravitation can be defined as an interaction between the masses. Okay, any two masses, however small it may be. Suppose we are talking about two protons, both are protons, and as you know, mass of proton MP is 1.6 into 10 to the power minus 27 kg. However small this mass is, even these two small mass particles, right, subatomic particles, protons, they too interact with each other because of the masses they have. Not only these small particles, this interaction is equally important or equally relevant, the discussions are equally relevant in case of interaction between bodies as large as sun, the star, you know, and Earth. Yes, between the huge bodies, and these two are heavenly bodies, right? These are subatomic particles. So you see, their masses are much larger than these two, right? But here they also undergo an interaction. This interaction is because of their masses. Say mass of the sun is capital M, mass of the earth small m. Because of the mass they have, they do interact. In electrostatics, if you remember, we have discussed it that two charged particles, okay, having charges Q1 and Q2, having a charge Q1 Q2, they interact with each other. This interaction is electrostatic interaction, and this interaction is because of the charge on the particles. Okay, neutral particles don't interact electrostatically. So electrostatic interaction is due to the charges on the particles, charges on the bodies. Similarly, gravitational interaction is because of the masses. Okay, and later on we learn the Newton's law of gravitation. Okay, Newton's law of gravitation is the official statement, a mathematical expression, okay, for not only qualitative, even quantitative study of gravitational interactions. So we will go in that detail now. Newton's law of gravitation. Newton's law of gravitation. Newton's law of gravitation. After a long span of observation, okay, usually this is said that when during the pandemic plague in England, in London, it was a lockdown like situation as we have today. Newton was forced to stay at home, and during that duration he observed the moon, its motion, right? And he observed that the rotation is periodic, that moon, and we all know that the motion is periodic. And on this periodicity of the moon's evolution around Earth, okay, is used to prepare the lunar calendar. That we all know, right? In all mythological characters, in all our mythology, in our Hindu calendars, in Islamic calendars, all are based on the lunar motion, right? They are called the moon's revolution, and that's why they are called lunar calendars. Okay, so you observe this, and definitely if the moon, see, for example, if the moon is there and moon is revolving around Earth, since and the orbit is supposed to be a circular or almost circular, right? The moon is revolving around Earth. Yes. Question is, when the moon has to revolve in circular orbit, that means moon has to execute circular motion. The question is, if the moon has to execute circular motion having an angular velocity omega, then definitely it is the question that comes in your mind. You must know that for any circular motion, right? For any circular motion, one force is must. The body must have this force. Okay, it must be provided to this force, otherwise the circular motion on a circular track is not possible, and that must be force is known as centripetal force. Centripetal force. Now the question is, what provides the required centripetal force? And the centripetal force is, definitely we all know that centripetal force acts along the radius and it acts along the radius and towards the center. That simply means Earth must apply an attractive force on the moon. Earth must attract the moon towards its own center. Okay, since this force this must be attractive, otherwise you can't interpret the existence of centripetal force. You can't be able to interpret the circular motion of the moon around Earth. Okay, so for centripetal force to be there, you must have a force that will provide moon the required centripetal force, and the answer is, what provides the required centripetal force? What is the source of the centripetal force? What applies the centripetal force? What provides centripetal force to the moon? The answer is attraction of the Earth. So we say Earth attracts the moon by force, say F. F is the force which acts on the moon, applied by the Earth. Okay, this is the force acting on the moon, applied by the Earth. We may write it FME, force acting on the moon, applied by Earth. From Newton's third law, you also know that forces are never alone. Forces are always available in nature in pairs, and the pair is called action-reaction pair. That means every force must have its reaction pair. So if this one Fne we call action, let us call it action. The action which is applied by Earth acting on the moon, there must be a reaction of this force. And you also know from the third law that action and reaction never act on the same body, they act on two different bodies. So if the action is said to be acting on the moon, we have to say the reaction must act on the Earth. And this is FEM, the force acting on Earth applied by moon. So these two forces, F and E and FEM. Both the forces pair together make action-reaction pair. So if FME we call action, then we must call FEM as its reaction. Okay. Let us have one more step. We also know that the action and reactions are always equal in magnitude. That means mod of FME is equals to FEM. Okay. FME is equals to FEM. That means their magnitudes are equal. And we also know in case of action-reaction pair that action and reactions are equal in magnitude, but they are opposite in direction. Since they are opposite in direction, we may write FME is equals to minus of FEM. Fine. So they are equal. their line of action is same, but opposite direction is opposite, and they have the equal magnitude. That simply the concept is really surprising, that because of the fact if you are saying that gravitational interaction, right? That was, so gravitational interaction is what? The interaction between these two bodies, okay, whose masses are quite large. Earth, obviously, a very massive body. Moon, another one, is a very large one, and they two interact. And because the interaction is there, and this interaction is must, because we know Moon revolves around the Earth, and it must be acted upon by a centripetal force, and this centripetal force is provided by the attraction of the Earth. Earth pulls the Moon towards the center. That pull of the Earth on the sun, Moon, is nothing but, or we can say, the centripetal force is provided by gravitational force. Gravitational force. And keeping in mind the different features of the forces, the properties of the forces, the action reaction properties, okay, we conclude that whatever force the Earth is applying, by whatever force the Earth is pulling the Moon, exactly with the same force Moon is pulling the Earth towards itself. That means Moon pulls the Earth as well as the Earth pulls the Moon. These two forces are equal in magnitude and opposite in directions. Okay. What is this? That is the equal. It means what? The force doesn't depend on the mass of the single body. It doesn't mean that. Okay. That means so you say the mass is massive. The mass of Earth, as you know, mass of Earth, okay, is much greater than the mass of Moon. Right. And if gravitational interactions are because of the masses, okay, you may confuse or you may develop a doubt in your mind that definitely if the Earth is massive, more massive than the Moon, then definitely the pull of the Earth is definitely more than that of the pull of the Earth is more than that of the Moon. Okay, but here since they make action reaction pair, it means their individual masses don't play that much role, or even of the fact is that mass of the Earth is much greater than mass of the Moon, but we have just seen that magnitude wise F and E is equals to F, E, M. Right. So we want to frame a basic law, expression. If you want to frame a mathematical expression for the gravitational interaction between the Earth and the Moon, okay, Newton observed, since the mass is the property behind or responsible for gravitational interactions, and we can say, okay, it is the mass because of which the gravity is there, gravitational interactions are there, but yes, you see, it doesn't matter whether the mass is more or large. Okay, if mass of the Earth is, as you have seen, mass of the Earth is quite larger than that of the Earth, but the pull of Earth is equal, just equal to the pull of the Moon. That means they pull each other with equal forces. Okay, so how to make a frame? How to frame it? So frame, forces, F interaction, F. Say this Fm E or equals to Fem. We have seen, and say this magnitude is F. Say, okay. Actually, F should be. How to make a formula expression and mathematical that expression must satisfy the experimental results. That to be kept in mind. And finally, after law of experimentation, it will establish that this force is proportional to product of the masses. Product of the masses. Product of masses. You may say mass of the Moon as small m, mass of the Earth capital M. We may write F is equals to capital M into small m. F is directly proportional to product of the masses. See, since product It is the only mathematical operation that will give you an advantage, and that will give you a chance to explain this feature, whether that they will, even their masses are different, they will interact with equal forces. That means the force applied by Earth on the moon should be equal to the force applied by moon on Earth, and that is possible only when their masses are, therefore the force between them is proportional to the product of their masses. Second, as this force is, it was observed that the nature of the force is conservative. Nature of the force is conservative. Why? Because you will never see that the moon will jump off the orbit. It will never go off the orbit. That means in every one complete revolution, if it completes the revolution, right, there must not, you can say, after one complete revolution, after one cycle of revolution, you must see that you must make it sure that there should not be any loss of its energy. No loss of energy means no mechanical work done. That simply means the work done by this force in a round trip must be zero. If it is not, then the moon will lose its energy, and gradually after losing energy it will start revolving not in circular but in helical orbit, and finally moon should drop in the earth. But that doesn't happen. We can see from thousands and millions of years, moon is doing the same. Moon is moving up in this orbit, and this orbit is said to be having a specific value of energy. So moon doesn't either go away nor come close. It moves in stable orbits, and the orbits of the moon is since stable, we can say what? The force or the energy of the system is conserved. The total energy of Earth and moon system is conserved. No change is there, and that means the forces are mostly conservative. This force is conservative, and since it is conservative, it must obey inverse square law. Inverse square law. So F is proportional to 1 by r square also. Combining these two, we can write F proportional to m into small m upon r square. Okay, how is it? So by satisfying the concepts, satisfying all the things which we already know, we can frame a very easy relation for expression for gravitational force F. So gravitational force F between two masses m and small m, capital M and small m, and separated by distance r. The distance separation between these two is r. So this is what F proportional to m into n by r square, and since these interactions are quite weak, obviously very weak, so after putting the values of known masses and known r, Newton noticed that this doesn't match. If there is no constant of proportionality used, okay, definitely, and if you put masses only and the distance r, you will not get the exact value of the force. Reason is what? That means there must be a constant. And one more thing, that whatever constant we have put over here, if we just put a dimensionless constant over here, just to remove the sign, proportionality sign, you'll see that equation will not be homogeneous, or it will not be dimensionally correct. That means there must be a constant which must be there here in place of just on removal of the proportionality sign. We must put a constant, and the constant must be of certain magnitude, as well as it must be a dimensional constant. So it should be a dimensional constant, otherwise there will be a problem in homogeneity of the equation. So the constant must be a dimensional constant, and not only that, it must have a specific value. Later on, so many people measure this value, and we call it capital G, called universal gravitational constant. So F is equals to G into m into small m divided by r square. Okay. So according to this, apart we have seen, and the value of G, what is G called? G is known as universal gravitational constant, whose value 6.67 into 10 to the power minus 11 Newton meter square per kg square. Newton meter square per kg square. That is what the value of capital G. Okay, after series of experimentations, it was also observed, Newton noticed that since we have discussed the interaction between the moon and the earth, okay, but what is the rule or what is the law of nature for two small particles? Say of course some grams, milligrams, okay, and so on, even in small fractions of this. So what are the rules? Newton noticed that yes, there is a common law of nature, okay, for whatever be the mass of the interacting bodies, these two masses, say mass m1 and mass m2, and these two are separated by distance r, okay, they will interact with each other, and the forces are equal. This is the force F1 acting on M1, this is the force F2. Newton expressed, as I have seen in the case of moon and the F1 equals to F2 and F1 equals to F2, say F is equals to G M1 into M2 upon R square. That is the expression for this. Now you see, if the particles are as smaller, as lighter as electrons or protons, subatomic particles, the law of gravitation still holds good. Second thing, in a basic difference between the gravitational interaction and electrostatic interaction, you should not forget the interaction between the charged particle is called electrostatic interaction, and when two charges, see the expression, the difference, when two charges, say Q1 and Q2, when they are separated by distance r, this is the force acting on one, say F1, this one is F2, here also F1 is equals to F2, and this F is given as F1 equals to F2 equals to F. So F is equals to 1 upon 4 pi epsilon naught. If these charges are placed in vacuum, there is no medium, okay, free space. So this is expression for the interaction, the force between them is given by 1 by 4 pi epsilon naught into Q1 into Q2 upon R square. This epsilon naught is for vacuum and for any medium, F in a medium is given by 1 by 4 pi epsilon or epsilon R into epsilon naught into Q1 into Q2 by R square. This epsilon R is called relative permittivity of the particular medium. That simply is clear that F in a medium for electrostatic interaction, F in a medium is F in vacuum divided by relative permittivity of the medium. So it is obviously maximum, the interaction between charged particle is strongest in vacuum, and in any other medium it goes less. Here as the case is different. Here the constant G is called universal gravitational constant. The reason is this gravitational interaction is independent of the medium in which the mass particles are kept. The bodies are kept. The medium between the two interacting bodies, whatever be the medium, the gravitational interaction will be as usual, right? Whether it is vacuum or water or gas or whatever medium, right? The gravitational interaction between two masses will be, okay, no difference. And these kind of interactions are medium dependent. Okay, it's maximum in case of vacuum. There is no medium, it's free space, and it decreases when there is some medium. The medium comes between the charges, whereas this is independent of the medium. The second fundamental difference between the electrostatic interaction and gravitational interaction is electrostatic interactions can be. Electrostatic interaction depends on nature of the charges too. What does it mean? It means if the charges in question are, both of them are positive or negative, that means like charges. In electrostatic there is a law of nature which says what? Like charges, we know well, like charges do what? They repel each other. And opposite charges do what? Opposite charges attract. Whereas means they pull each other, or they can pull or push, right? Both are possible when the charges are like in nature, both of them are either positive or both of them are negative. This kind of things are there, means they will repel, but if one of them is positive, other one is negative, rather than repulsion, they will do attraction. Whereas in gravitational, in case of masses, interaction between the masses or gravitational interaction, we see what? Since the mass has no such nature, you can't classify the mass of one object with the other on the basis of the nature like charges, and so we can say what? The force between the two mass particles is purely attractive. Purely attractive. The sign convention wise, this is the process in physics, that by convention, by sign convention, the attractive forces, we know well, attractive forces are said to be negative forces. Attractive forces are called negative forces, whereas repulsive forces are called positive. Yes. So in case of electrostatics, the force can be either positive or negative, whereas in case of mass particle, the force is going to be strictly negative. That means this is only attractive in nature. Okay. Now see a small fraction over there. See a question. I am just giving you a question right now here. Say a large body of mass capital M is taken. If the body is broken into two lighter mass particles, okay, one, okay, of mass M, then definitely other is of mass M minus M. The question is, okay, what should be the magnitude of small m? Find the magnitude of small m so that the attraction or gravitational attraction, so that the gravitational force between them, what should be the value of small m, so that the gravitational force between these two will be maximum. Force will be maximum. That is the question. What should be the value of small m, so that the force between them, the F, whatever the F should be F max. Okay. How to solve this question? Write down the gravitational equation, the equation of Newton's law of gravitation, the mathematical form F is equals to G. And the masses are small m and m minus m, this upon r squared. Okay, this F is going to be maximum. See, there are two things. They are silent about R. They are not talking about R. We'll come to it later on, right? This force is F expression. F has two parts, a fractional one, having a numerator as well as a denominator. But in the question they are raising no doubt, no question about the distance between them. Whatever with R, they are just discussing about how this larger mass M is distributed to get the maximum interaction between these two fragments. Okay, so here I can use this one, and this will be G m into small m minus m squared, and this upon r squared. So if F2 maximum, F2 is to be maximum, you can understand the simple logic that the numerator is to be maximum. That means m minus a small m square, say y, and that should be maximum. Okay. If y should be maximum, using the laws of maxima and minima, I can differentiate y by small m. So dy by dm and the first derivative, okay, must be 0. That is the principle of maxima and minima. So dy by dm is, dy by dm will be, find out dy by dm, it will be small m minus 2 small m, and that should be 0. If I want to check it is maximum or minimum, 0. That means twice m is equal to capital M, or small m is m by 2. Small m is m by 2. That means the interaction between the two particles placed at a certain distance is maximum if they have equal masses. Right? This is the maximum. Here also this body of mass m was right, and now their masses is small m is m by 2. The new masses are m by 2 as well as m by 2. The second feature, let us say the denominator part in the expression. The denominator part says what? That this m is proportional to 1 by r square. That means if the masses are kept constant, definitely the f values with r in this way, or we can write down f1 upon f2 is equals to r2 square upon r1 square if r is changed. When for distance r1 the force is f1, for distance r2 and the force is f2, we can explain that relation. And since f is inversely with r square, it means for a system of two particles, right, if the force and r are plotted against each other, in y-axis they will plot the force of interaction, gravitation interaction, and r the distance in the two mass particles. And since f is inversely with r, we have a rectangular hyperbolic curve which is f proportional to 1 by r square, and that tends to r-axis where at infinity, and r is equals to infinity. That means, okay, and it will be 0. It will be again, f will be infinity again when r is 0. So that is another thing. So we can say what? This force f tends to 0 when r tends to infinity. So conclusion is very clear that if distance get double, distance is double. If we just get the double, the force between them becomes 1/4. Okay, and f, since we have noticed the curve is that hyperbolic curve, f tends to 0 when r tends to infinity. We can say what? The theoretically even that the force, the gravitational force, has been a large domain of activity, of action, or we can say this force is active up to infinity. That means this is a long-ranging force. And as in the beginning, I have made clear that this force is what? Conservative in nature. Work done. So work done in round trip, okay, by the force will be 0. Since work done by this force is 0. As conservative in nature, long-ranging forces. These forces are long-ranging because of the fact that f tends to 0 and r tends to infinity. Okay, theoretically, even the force is quite weak. You can't notice even from this short distance, but theoretically, these forces extends up to infinity. Now, when we are talking about this force, the next topic is, you have seen that two mass particles, when they are pulling each other, they are necessarily not in direct physical contact. Okay, that means these interactions are possible even from a distance. For this, the physical interaction is not required. This interaction can remain intact, this love between them remain intact even when they are in social distancing. So they can attract each other like that. Wow. How is it possible? Just that is possible means that is possible because the interaction is through what? You know, you have learned in the chapter. I had told you in detail in the first chapter, Newton's laws of motion. While introducing you to the world of forces, we have made it clear that there are so many forces in nature. Few of them need to be in contact. Okay, when they are applied, and secondary forces which don't need any physical contact, they can be applied even from a distance. So this is what a type of second type, where it is possible to pull another mass particle. Okay, by one mass particle, one body, it can pull the another one, even from a distance, even from a large distance, right? You can see. But how is it possible? These forces from a distance are also called field forces. They are called field forces. Okay, that simply means it is very much similar to the field as we have discussed in electrostatics, where the charges do create a region, an area, domain of their influence. Okay. Similarly, the mass particles, the masses also have their own domains of their region of influence, in which if they interact, any other mass comes over there, remain present. Okay, this first mass particle is going to pull the second one. Okay, and these interactions are made possible by this agent. Okay, which is medium. This is what they call field. So these forces are field forces, and so gravitational force is also field force, and there is a field around the mass particle like a charge. This field is called gravitational field. Gravitational field. Okay, it's very simple to understand. In this chapter, we have started the basics of law of gravitation, and next time when we meet, we'll continue this, okay, and discuss the existence of the fields and their behaviors and some problems in that one. Thank you.